Hello guys, good morning. King, Ammar, and Dylan. Can you all hear me? You can use the chat to respond if you want. Thank you, Dylan. Okay, can you see my screen as well? I'm sharing the slides for today, the first substructure lecture, we have two topics today, the soil formation and the soil classification. Okay. Please let me know in chat if you have any query or you have any problem or you can't see the screen or you have problem with the voice. We'll just wait few minutes until other student join us. Okay. During that, I will share my other screen, which is showing the website of the course, Structure 2. As you know, we have two components of this course, superstructure and substructure. And here is the two links for the Zoom session for the two lectures. And also you can here see the timetable of the course, two components of the course. Okay. And here on the left, you can see the content of each week. Here for the superstructure part, there is 4 weeks content are shown, and up to now I have only shown one content from the substructure part. And if we click this link, you can see the objective of the first lecture and the tasks we will be doing today. And here is the presentation or the PDF file containing the course content for lecture 1 of the course. And I have also added some summary videos so you can refer back when you after you attend the lecture. It is recorded from previous deliveries of this course. And also I will be adding the recorded lecture here, somewhere here on this page. You can also find the recording of this lecture under the recording section here, under Zoom session or Zoom recording. Up to now, because we haven't recorded any lecture yet, so it will be here in the recording section. Okay, so the content of the course can be found here. The link in the welcome page, the link to join the Zoom session on the welcome page. And I have already shared the PDF we will be discussing today. I hope you are seeing it now. Do you have any question, guys, before we start the lecture? Any one of you from Wednesday 1 p.m. class? I want also to apologize for not attending the class this week for superstructure part at 1 o'clock because due to unforeseen condition, I couldn't attend on time. So I canceled the class and I will make a makeup class for you. So we can discuss after the lecture what is a suitable time for a Zoom session to make up this missing class. Okay. Sorry again, guys, for not attending this week. Actually, I attended by late. Sorry for that. Okay. Think we can start now the lecture. So I will just close my video, stop my video, just to be able to use my whiteboard screen. Okay, so now for the substructure part, we have the substructure part of the course. Okay. It is about 33% of the total grade. So you have 66% for the superstructure part or component of the course. Okay, so this lecture will be discussing the substructure part, and today we have two main topics to discuss. The first one is what is the soil and how the soil forms. So we will be talking about the formation of soil. So if we go to the next slide, before we start, this is a welcome page to the course and like introduction of myself. My name is Ahmed Cheta, and I have a PhD in structural engineering, and my location at Mosul Lakes campus. And this is my email if you need to contact me or you have any query. So you can use my email to send any query, and I will try to respond as soon as possible. Okay. And here is the lecture for the substructure component of the course. We have 10 weeks, so 10 lectures. Each lecture is 2 hours. The lecture will be on Friday from 9 to 11. These lectures are recorded and will be uploaded to the website, to the Learn Online website. Okay. And also there will be 30 minutes of consultation every week after the lecture. So if you have question, I will be in the Zoom session to respond to your queries. And also if you have any queries during the week, you can send me and I will try, if needed, we can make like additional Zoom session to discuss. Okay, there is no, also for your information, there is no tutorial classes for this part. So the tutorial classes only for the superstructure. The substructure part will be only the lecture, and you can discuss the problem if needed during the lecture itself. Okay. So this is just introduction about myself and about the lectures time. And the next slide is a table of content of the semester and also the assignment we have. So we have again 10 weeks lectures. We are off in week 5 and also we start from week 2. So we don't have lecture on week 5 because it is a public holiday. So we have 9 lectures and we have in the middle 2-week breaks, no lecture. So we have these topics. First topic, origin of soils and soil classification that we will discuss today. Next week, soil behavior, and so on until week 11 we have pavement, and in week 12 we will be doing a revision or exam revision before the final exam. Okay, the assignment for this course or the assessment of this course, we have only 2 assessments. The final exam, which is from 50% to 20% of the total grade. Okay, and assessment of the substructure is 15%. So we have about 30 to 35% of the total course. As I mentioned, it is 33%. So the weight of the substructure part in the final exam will be about 15 to 20% of the total grade. The assignment 1 is due on Friday, 10th of May at 5 p.m., which is week 11. So it is Friday, week 11. So after we finish all the content of the course, there will be the due date for the assignment. Okay? So you have plenty of time to finalize your assignment and do your best to get higher marks. Do you have any queries up to now? And is the voice is clear and you can see my screen clearly? If you can just confirm with me in chat and try to be interactive during the lecture. Okay, thanks, Ammar. Okay, so now after we know the content and the assessment, we can now start our discussion about the soil investigation and geotechnical engineering. As you know, the substructure part is related to the soil investigation, which is important to you as a construction manager, because as you know, when you are a construction manager, you went to the site so you need to know what is the soil type, to know how to deal with the soil and how to treat the soil if it is need treatment and so on. So the geotechnical engineering part is quite important to a construction manager or as engineer to understand what is the soil and if there is any problem with the soil, so you know how to deal with this problem. Okay, because as you know, all our structures like the shed and superstructure is supported by the ground. Even if you have underground like tank or something, it is still resting on soil. So all the structure resting on soil or ground, most of them, like, because the other option is the structure rest on water, which is floating structures. But for like 99, 95% or 98% is supported by the soil. That's why soil investigation is crucial for us. The load carrying capacity, which means how much the soil can sustain from the applied loads. The load carrying capacity of the ground depends on its mechanical properties. So this also one of the importance of studying the mechanical properties of the soil, to know exactly how much the load carrying capacity or how much is the load that this soil can sustain. Because as you know, some of the soil are weak soil or soft soil, so they cannot sustain loads. Okay. We need also to understand the soil behavior for design and construction and managing the project risk. So understanding the behavior will help us to avoid problems or avoid risks, and also will be necessary for our design. For example, we have two examples of neglecting the soil investigation, which lead to a disaster or problem in the structure. As you can see here, this is the Ibiza Tower, which is leaning Ibiza Tower. Do you know what happened to this tower? This tower, because the soil here was weak, so the structure settled from one of the sides of the two sides. So actually it was overturning during the construction because there was no soil investigation for this site before starting the project. Okay. And to avoid collapsing of this structure, they try to add some weights here to manage to keep the center of gravity of the structure in the middle. So they try and spend a lot of money to just keep it stable or not collapsing, preventing it from collapsing. However, if they have done a proper soil investigation before starting the project, they may have avoided this. Okay. Another example is the airport in Japan. Also, they didn't do investigation of the soil before starting the project. So sorry, you can use this one. So the airport sink in the soil. Also because of the weights, and the soil is not strong enough to support the load. So the airport sink or settle from some sides of the structure or of the airport itself. So these are two important example of settlement of soil because of neglecting the soil investigation before starting the project. This airport is called Kansai Airport in Japan. You can make your own search about this and see what happened and have some information about that. Okay. Any question for that? We go to the next slide to start to know what is the soil. What is a soil? A soil is a solid particles containing gases and liquids in voids. So the soil is some solid particles associated with gases and liquids entrapped in voids. So as you can see here, this is soil. You can see these are the soil particle or solid particles. And we have this blue is liquid and mainly water. And we have also some white holes which indicates air voids or voids. Okay. Or we can generally put it as gases. So because the air is considered as gas or the air contain gases, so we have gases in this voids. Okay, so generally this is the definition of the soil. So it is some soil particles, solid particles associated with water and air. So if we try to analyze this soil, so if we accumulate all the solid part together, so they will give us the volume, this volume of solid. And if we accumulate all the water together, so we have also a volume of water here, V water, and so on for the air. So we have V air. So we can just accumulate all the elements together to have three elements: water, solids, and air. That's why the soil is defined as three-phase material. Three-phase material, what are the three phases we have? Solids, water, and air. Okay, so if you are asked how many phases for soil, so the soil is three phase. Okay, do you have a question here? No question? Just try to explain something to you here. So if we have here, so again, our soil, normal soil, is a three-phase material. Okay, the material, the three phases of the soil are, we have solid particles, which are the main part. And we have the water. And finally, we have air. Okay. Sorry, Joel, voids are like empty spaces, or if you have something like that. So this solid, all of this solid. So void means a hole or empty space. This is the definition of it. Okay. Okay, thank you. So now we have these three faces. The voids are here entrapped in the air are filling the voids. But because the air is weightless, so that's why we consider it as void. Okay, so now just to remove this one. Sorry. Now this was the normal soil. We have another type of soil, it's called saturated soil. We need to know what is the difference between saturated soil and normal soil. Saturated soil is soil and all the voids are filled with water. So there is no air voids. So how many phases will be this soil? If the air here, if there is no air here, and the air is filled with water. So what are the phases of this material? This material, right? Thank you, Ren. This will be two-phase material, and the material will be solid particles again. And the other phase is the water. So the saturated soil is different from the normal soil. That saturated soil is two-phase, normal soil is three-phase. Here, no air in the saturated soil. Okay? Do you have any question for that? So now we know how the soil, what is the soil definition and what is the phases of the soil. And now we jump to how to find some of the soil probabilities using the phase, the soil phases. The diagram we mentioned earlier is called phase diagram. Again, this is the solids, particles. So the soil mainly soil particles. Yes, the solid particles is any material like sand, gravel, rocks, and so on. But if you hold like a soil or it has some particles, solid particles, contain whatever the size of these particles, because the size of the particle indicate if it is like gravel or sand or silt or clay, and including in this soil we have some water and some air entrapped as well. Okay, so if we go to the phase diagram again, this is our soil phase diagram. The general one is for normal soil. So we have a three-phase diagram. So for the three-phase diagram, again, we have solid particles and water and air. To analyze this phase diagram, we need to know the mass and the volume for each of them, each phase of them. So for the volume, we indicate it by V. So Vs means V solids. M is indication for mass, so Ms means M soil. So for each phase or each component of the soil, we have V and M. V's are volumes, M are masses. So in the lab, in the soil lab, you will be able to find V and M for the three phases of the soil, okay? How can we use these phases? If we want to find the total volume of the soil, V total, we can add T here. So V total will be the solid volume of solid plus the volume of air plus the volume of water. For the mass also, for the mass, total mass is mass total equal to mass of solids, mass of air, and mass of water. So this already can be found directly from our measurement in the lab. We have some terms, technical terms we need to know for soil. The first one is the bulk density and dry density. and water content of the soil. From your previous study, what is the definition of the term density? Density is the mass over volume. So bulk means total. So if we need to find the total mass, the total density, sorry. So what is the total density? Thank you, Ren. It is the mass, total mass over total volume. So rho equal to MT over VT, where MT and VT from the previous step. We have another expression called dry density. Dry density, what is meant by dry density, if you can have a guess? Dry density means that we excluded the water, so we just focusing on the solids. So to find the dry density, rho d, it will be only the mass of solids divided by total volume, T. So if we want to find the dry density, you need to exclude the mass of air and mass of water and only use the mass of the solids. We have also another expression, it's called the water content. Anyone can mention what is the water content is? The water content is how many water inside this soil. So to find the water content, we will divide, it has the symbol W, the mass of water divided by the mass of solid. So to find the water content, water mass divided by solid mass. Okay? Do you have any question about that? So these are some expression or some technical expression or probabilities we can obtain from the phase diagram and from our measurement in the lab. Yes. Thank you, Ren, for your question. Here, for the bulk density, the volume is V total, the total volume of the solids, air, and water. Also for the dry density, we get only the mass of the solids divided by the total volume. So for bulk and the dry density, we use the total volume. Okay? Because we are calculating bulk and dry density of soil. So the volume will be V total, the total volume of the soil. Okay, thank you. So now if we jump to the next slide, these are some densities for different materials like water, clay, sand, gravel, concrete, to have idea how much the densities of the material. The density, again, has the symbol rho equal to mass over volume. And as you know, the mass generally measured, the unit is kilogram. The volume generally measured by cubic meter. So the rho unit is kilogram per cubic meter. This is the unit for the moment, for the density. If we look at the water has a constant value of density, which is 1000 kilogram per cubic meter. The clay has a range of 1500 to 1900. The sand has a little bit denser or has more weight. So it is 1700 to 2100. The gravel is quite similar to sand. So it is 1700 to 2200. And finally, the concrete. As you know, concrete is a mix of cement, sand, gravel, water. All of this together will give us a density of 2200 up to 2400. Okay. Just some notes here for the units. How to convert from kilogram to Newton. We have this before in the superstructure lecture or superstructure tutorial. To convert from kilogram is mass and Newton is weight. So to convert from mass to weight, you need to multiply times G equal to 9.81 meter per second. Okay? So to convert from 1 kilogram to 1 Newton, you need to multiply by 9.81. Thank you. But in some studies or in some areas, they try to simplify this. So they use the gravity acceleration as 10 instead of 9.8. So they round it up to 10 meter per second. So if it is rounded up, so 1 kilogram approximately times 10 will be 1 kilonewton, 10 kilonewton. So sorry, 10 newton. So this just accepted approximation is 1 kilogram. To convert from 1 kilogram to newton, you can use the multiplier 10. So 1 kilogram will be equivalent to 10 newton. And here it will, from 1 kilogram to newton, it will be 9.81 newton. Okay, this is just a small simplification for the units. Okay, here. Okay, so these are some examples of the densities of different material. For your information, you need to have also idea how much the densities of some materials that we are usually using. So if we jump to the next slide, we start discussing the origins of soils or how the soil forms. So do you have any idea about the rock cycle or this diagram here? So this diagram is called rock cycle. And as you know, most of the soils or rocks comes from this source, volcanoes. Okay, and then due to the weathering and temperature and wind and so on, this volcano rocks break down to, so the rocks broke down or break down to smaller particles, forming the soil. So the soil mainly come from rock and using or based on the rock cycle. So we have some type of rocks. Here is igneous rock, and we have also sedimentary rock, and we have metamorphic rock. So we have three type of rock. The main one is igneous rock. So the magma or the melting magma crystallize and form the igneous rocks here. So this is our first type of rock. And due to here weathering and erosion and deposition, it caused our soil or sediments. So sediments is the soil particles. So this is the main source of soil on Earth, from magma crystallizing and form the igneous rocks, and then after weathering and erosion, wind and deposition, it caused the sediments or the soil particles. Okay, then sediments again accumulate and form a type of rock called sedimentary rocks and repeat the cycle again. But the main one is the igneous rocks, which formed by solidification of molten magma ejected from deep within the Earth's mantle or volcanoes. Okay, the second type of rocks we have is the sedimentary rocks, which deposits of gravel, sand, and clay, which are the soil particles we have on land. By weathering, also compacted, cemented by overburden pressure and cementing agents like iron oxide or calcite. Okay, so the idea is we have a big rock. This rock like cracks and form smaller particles. These particles are gravel, sand, clay, silt. Okay, this happened because of weathering or wind or different temperature and so on. After many years, this process also takes millions of years or thousands of years. Okay, but a reverse process happened when these particles like accumulate together again under pressure of soil or reactions with other cementing agents. So they cause some of the rocks called sedimentary rock. So we have the original process is forming the igneous rock, and then a reverse process to form the sedimentary rock. The last type of rocks we have, or the third type of rocks we have, is metamorphic rock, which formed of new type of rocks, changed composition and texture without melting by pressure and heat. So this means that we have the original rock without any weathering, and under weathering condition as well and high pressure, this become one rock. So they without melting, they become they accumulate again and become one rock. Okay, this process is called metamorphism. So this is generally the types of rocks we have, and we go to our next slide to know about weathering. So our common rock again is the igneous rock, and it is converted to soil particles by weathering. That's why we need to understand the weathering. The weathering is process of breaking down rocks by mechanical or chemical processes into smaller pieces. So again, we have big rock. After weathering, it become small particles due to the weathering condition. We have two types of weathering. It can be called mechanical weathering or physical weathering. We have many types of physical weathering, and this is the common one. So most of the rocks formed due to weathering or mechanical weathering. For example, we have the temperature difference, water freeze thaw, glaciers, and running water, and 5 wind. Okay, I will just try to add a slide here to explain that. Okay, so here the temperature, we have temperature difference, just explaining how the temperature difference causes weathering or rock breakdown. For example, we have a big rock, and during the evening time, so the rock is cold or under cold temperature. Under cold temperature, this is during the evening. And during the day, there is sun and high temperature. So the outer surface of the rock will be under high temperature due to sun or due to morning time or daytime. And inside the rock, for example, this part, so this part is hot and this part cold. Due to the difference between the hot part of the rock and the cold part of the rock, some cracks happen here. So we have cracks in the rock. This process happen over thousands or millions of years. So due to repetition of this process, these cracks increased until they meet here or here, and this rock break down to smaller parts. Okay, so this is what is meant by temperature difference. And if we go back here, so this is temperature difference. The next one is water freeze thaw. What is meant by water freeze thaw? Again, here, if we have a rock and there is some cracks in the rocks, big rocks, the water get into this area or this crack. Then due to low temperature, this water freeze. So when it freeze, it expand or volume increase. So what happened to the crack? Crack increase. So the water get into the cracks in the soil and freeze and then expand. When this water expand, what happened to the crack? The crack increase until it break down the soil to two parts. Okay, so this is how the water freeze thaw go. And you have glaciers. Glaciers are the snow or ice when it's accumulate together. So it can also cause weathering to the rocks. And we have running water and wind. So all of these types of weathering are mechanical weathering or physical weathering. The other type of weathering we have is the chemical weathering. This one is less common on Earth or rare, but it happens. The chemical weathering is we have rain, and the rain sometimes it contain acids or become acidic water. When the acidic water go to the touches the soil, the rock. So we have acidic water, and this water also come from here. This is the process of acidic water. So due to carbonation with the rainwater, it become carbonic acids. This carbonic acid, when it go to the rock, it goes because the soil has mineral inside. This mineral means it has calcium or magnesium and so on. So the acidic water react with the minerals inside the rock and cause soluble salts. So these soluble salts are a result or product of the reaction of acidic water plus the mineral. These soluble salts are soft and cause the rock to break down. Okay. So the chemical weathering means that the rain, due to the rain subjected to CO2, it become carbonated or become acidic. Then the acidic water react with the mineral inside the rock and causing soluble salts. These soluble salts are soft, so it causes the rock to break down into parts. Okay. So all the weathering process means that the big rock or the original rock break down to smaller parts. Okay, do you have any question for weathering? Just before we shift to the next step after weathering? Any question? Any query, guys? Nothing? Okay, so after weathering, so now the rocks are break down to parts. The next step is after weathering. What happened after weathering or after rock? The big rock become smaller particles. So after weathering has broken down the rocks into discrete soil particles. So this is called discrete soil particles. There is two options or two scenarios. The first scenario is the soil stay at the source location and will be called as residual soil. So if the soil remains on original location, so it become residual soil. The other option is the soil transported by gravity or wind, water, or ice, and will be called in this scenario as transported soil. So the transported soil that moves to different locations by water, air, gravity, glaciers, and so on. So the soil didn't have two scenarios again, residual or transported. Okay, as you can see here, this is our parent rock or the rock before weathering. After weathering, there is small particle somewhere here. The wind will take this particle to a different place, or if we have also like river here somewhere, so this soil move from here to here. So this soil becomes transported soil. What you expect? What is the common type of soil we have on Earth now? The common type we have is transported soil because of the weathering and the weathering, and after the weathering we have the wind blowing and water running and ice and so on. All these conditions move the soil particles from place to place. So during the year or ages of the year or ages of time in on Earth, like thousands years, millions years, this soil has transported many times and the soil profile changed. That's why when they dig a bore on the soil, they have different layers and different soil types. Okay. So now we start the definition or understanding what is the residual soil. Again, residual soil, the soil remains on its original location. So this soil are developed in areas of stable topography through oxidization and leaching of the parent rock. So this happened in the stable topography, and due to oxidation and leaching of the rock, we have the residual soil. Again, we have here the parent rock, and the top part of this rock has under temperature or freeze thaw of water. It weathers or it is under weathering, and the top part is the soil remain without any movement, so it become called a residual or residual soil. Okay, so we have, this is our rock already. And the top part of this soil or this rock, because it's still remaining in the same place, so it is called residual soil. Okay, what do you think the relation between the parent rock and the residual soil? Are they having or holding same properties or different properties? Because the residual soil and parent rock are from same type of soil, so they have similar soil properties. So there is not much difference in the properties because they are from the same type. The other soil type we have is the transported soil, which is more common. So we have the transported soil or the more common type. The transported soil, again, is the soil that move from its original location to different location or to new location. Okay, this type of soil occur in areas of topographic instability. So the other type of soil, which is residual soil, was in stable topographic areas, but this one happened in the or occur in the topographic instability area, and the soil thicknesses often bears no resemblance to the underlying bedrock contours. So the soil or the transported soil depths doesn't reflect the depth of the rock underneath. Okay, because they are not from same type. That's why there is no relation between them. Also, if we consider the properties of the layers, so this is our parent rock or our original layer, and this one is the transported soil or the transported layer. So is there any relation and properties between these two type of soils? Because they are originated from different soil type, so they have different soil properties. Because the parent rock originally was here, but the transported rock coming from another place. So the transported rock or transported soil, sorry, transported from a different place or different location. That's why they cannot have same properties. Okay. For example, here, if we look at this diagram, if we have a rock here, so this rock was weathered to small particles, and then the wind moved this particle to this river. So the river or the water takes the soil away somewhere here. So here will be transported soil. So the soil was transported from this area far to this far area. So this is what is meant by transported soil. There is another classification for transported soil. So the transported soil are sub-classified to different classification depending on the transporting media and where they are deposited or transported. Okay, so we have two criteria for classification of transported soil. One is the media of transport, like water, air, gravity, soil, and the other is were deposited. The final location. So media and the final location. We have 5 types depending on these 2 classifications. We have alluvial deposits. We have estuarine deposit, marine deposits, alien deposits, glacial deposits. Deposits mean soil or soil particles. Okay. The first one, alluvial, is by water and in lakes or floods. The other one, estuarine, is, we will discuss this in details now, but just briefly. When the river, estuarine is when the river reaches the ocean. So this is at the mouth of the river when it reaches the ocean. Okay. Marine itself at the ocean, close to the ocean itself. Okay. And glacial at the glaciers and so on. So if we go now in details about the definition of this type, these 5 types. So again, these types depending on the transported media and the location of deposit. The next slide is in details going through each type of this soil. For example, or the first type we have is the alluvial soils. So the alluvial soil are soil that formed by particles transported by water. So the main property or the main definition of this type of soil, it has been transported by water and deposited in lakes. So it will be deposited in lakes or floodplains. These soils are often sorted to sands or clay by the moving water. So they are fine soils or like smaller size particles. So this type of soil, the size particle will be small, clay or sand or silt. Okay. And also this type of soil has some subcategories. Fluvial, if it is from river or will deposit in a river. Pluvial, if it is deposited in high rain area. Laxatrine deposit if it is in the bottom of the lakes. Okay, so these are division of the soil or subcategory of the alluvial soil. And then the next one is the estuarine deposit. For the estuarine deposits, as you can see here, we have this our river and this our ocean here. So this area, in this area, when the water flow, smaller or fine particles will be deposited here. And causing the estuarine deposit. This fine particles can be considered as muds because it is clay plus water, so it is mud or fine particles. So these are muds with some coarser sized particle deposited in estuarine stories. Coarser size indicating the sand, because sand is coarse compared to the clay, but not coarse as much as the gravel. Okay, because the sand is that small and the gravel that small, so this is fine compared to this one. The bigger size is coarse, the smaller or the finer size is sand. Okay, what is estuarine? I just show you just a second. I will share another screen now. Can you see the picture? Okay. This is the estuary. So it is the area connecting the river with the ocean. So this is called estuary, and the water or the adjective of this is called estuarine. So estuarine is the water and soil deposited in this area. Yeah, the area between, like the entrance of the ocean from the river. This is called estuarine because the water here has different properties than the river because it is not running as the river and also not as the ocean because the ocean has floods and yeah, and the fluvial is the river, right? So the fluvial is the running river here, if you can see my mouse, and this is the ocean, and this is the estuary. So here, if you can see, there is some deposits here. It's called sandbar, and in this area, because the water is not moving that much, or the speed of the water is not high, so some of the soils are deposited here. The soil deposited here has different properties and called estuarine deposits. Okay, estuarine just adjective or related to estuary. Estuary is this area here in the screen on the screen. Okay, no worries. So if we go back to our slides. So this what happened in the upper estuarine. In the lower estuarine, so this is very closer to the ocean. So we have here coarser size particle. Okay. So in this area, we have coarser size particle because we have here ocean. The ocean has waves. As you know, ocean has waves. So the waves are going in this direction, and then sometimes it return back to this direction. So when the oceans return back, it causes some sediments, of course, size particles. So because of the ocean waves, it returns some of the coarse size back again, and this coarser size like sediment in the lower estuarine. So we have upper estuarine and lower estuarine deposits. Okay. Now, if we go to the next slide, we have the marine deposits. The marine deposits are offshore deposits and horizontal strata of silt and clay. So the marine deposits will cause strata of silt and clay. Silt and clay again are fine size particles. And the strata means that we have layers. Okay, so this is strata. So we have strata of silt and clay. We can also call this as ocean sediment. So it's called marine deposit or ocean sediment. Okay, this soil accumulate on the sea floor. So if this our sea, so somewhere here will be this our soil and this is water. So this will be on the sea floor. So this type of soil will be on the sea floor. And because of the silty water, this soil type is flocculent. because the water is salty, so it is flocculent. Flocculent means it is loosely aggregate or soft flakes. So it has some like smaller flakes like that because of the salt. So this soil will be on the sea floor and will be flocculent because of the salt. Okay, if you want to have also a look here, I have prepared some photo for it. So I will share my screen. If you can see this photo here, so this is the sea floor, and this is the flow of the water and moving the soil, and the soil finally will be deposited or accumulate on the seafloor here. So this type of soil is called the marine deposit or ocean sediment. Okay, do you have any question about that, guys? No? Okay, so if we return back to our slides, the next slide. We have some explanation of the soil transported by water. Okay, and this is example of or explanation of how the soil size dependent on the place of the soil and also the speed of the water. So here, if we are on the mountain here, so the water flowing this direction, so the water speed are high on the mountain, high water speed on the mountain. That's why in this area, very close to the mountain, we have the larger size of particle. Then when the water move, due to the obstructions, the water speed decrease. So what you can see when the water speed decrease, also the particle size decrease. So here we have the boulders or cobbles, and then gravels, and then sand, and then silt, and then clay. Okay, so when the water speed decrease, also the particle size of transported soil decrease. So when we close to the mountain, we will have the boulder size particle, and then when we go down up to the ocean, we have smaller size. So the boulder is the largest, gravel less large, sand smaller, silt smaller, and clay are the finer size of soil. Okay. So do you understand the idea of sedimentation of the soil? So when the soil, the water speed high, it sediment the larger particle. When it is slow, so it sediment the smaller particles. Okay, this all about the transported soil by water, and the next we have Ulian deposits or wind-blown deposits, which is transported by wind. This type of soil will be in the sands, in the deserts and beaches. So this type of soil in the dry areas, and the wind can only transfer or move dry soils. Why the wind cannot move wet soil? Do you have any idea about that? So if we have wet soil, the wet soil has larger weight because of water. The water add weight to the soil. That's why the wind cannot move the soil. Yes, heavy. So if it is heavy, so the wind cannot move it. So the wind can only move the lighter soils and the dry soil. So wind can only erode sand. That's why it cannot erode gravel or boulders because it is heavier. It affects are mostly restricted to certain climate areas such as deserts and beach. So it is only in the dry areas. Deposition occurs when the wind drops in velocity. So when the wind high speed, it will not deposit. When the wind stops or lower speed, it will deposit the soil particles. So all the time, the deposition of a lower or smaller size particle happen at lower speed. Okay? Wind can transfer fine sand, however, its effects are mostly limited to dry cells and in arid region. So this is the most common one. Dry silt in arid region or dry region. Because cohesive soils are resistant to the wind erosion. Why cohesive soils are resistant to erosion? Because cohesive soil will be heavier. So the cohesive soil and moist soil are heavier than dry soil. That's why they cannot be moved by wind. Okay. The last type we have of soils of transported soil are glaciers deposits. Glacier can transport particles ranging from boulders to clay, also known as till. If we look at this image here, this is soil moved by glaciers. So as you can see, we have bigger size of soil, which called boulder. We have also smaller ones like this one are gravel. We have also this as sand. So the glacial deposit can move all the size particles, all size of particles, such as boulders, the large ones, and the gravel, the intermediate one, and sand, and up to clay. Okay, so this is all the transported soil types, and now we have finished the first part of our lecture. But the next slide is just a summary of what we have done this part, and then we will have a short break. So what we have done in the first part or the first topic of the lecture, topic 1, which is soil formation, how the soil form or what happened to form the soil. So this is the summary of what we have done. What is the definition of the soil? We have three-phase material. If it is normal soil, water, solids, water, and air. It can be two phases only if it is saturated. How the soil is formed from the rock cycle. Different type of weathering. We have two type of weathering, mechanical and chemical. And under mechanical, we have various types. Different transportation media of soil. We have also water, air, and so on. How do particle size of soil vary depending on how it is transported? As we mentioned, the wind can only transfer or move the finer parts. Glaciers can move any size of particles from boulders to silt or clay, and so on. So this is a summary of what we have done up to now. And do you have any question, guys, for this discussion up to now? No queries? Okay, so we will have a 5-minute break. So up to 10:25 a.m. Then we will back to discuss our second topic today. Okay, see you in 5 minutes. Thank you. Hello guys, I'm back. Are you here? Okay, so now we'll shift to. Are you all here? So I can start. Don't want to start to the anyone attending. All good to start? Okay. So now the second topic we have today is soil classification. So first topic was about soil formation. Now soil classification. As you can see here, there's two types of soil. To the left is sand. To the right is clay or silt. Okay. So we need to know how to classify soil because this will help us in the soil investigation. We need to know. So the second topic today is classifying a soil or soil classification. In general, soils that contain clay are cohesive soil. So clay will make the soil cohesive or has cohesion. That's why when it is added to water, so it becomes very sticky. Soil with no or low percentage of clay will be non-cohesion or non-cohesive or cohesionless soil. So no clay or less clay, so cohesion or cohesive less soil. Non-cohesive soil or cohesion less. That's why when we look at these two figures or two images, we have sand. The sand is considered as cohesion-less soil because no silt in it. Sorry, no clay in it. And the clay is cohesion or cohesive because this is one of the property of clay. If I ask you how to differentiate between sand and clay. The sand are, if you hold the sand, so it is non-sticky soil because it is non-cohesive. But the clay is sticky because it is cohesive. Also, if you add water, so still non-cohesive after adding water. It will not be very sticky and you can break the soil easily. Non-cohesive. But if you add water to the clay, so it become very sticky as in the image. Okay, so this is stickiness before, or this is thickness before because of the cohesion. Okay, if we go to the next slide. In geotechnical engineering, we have many ways or many classification system. So we have some systems to classify soils. For example, we have the unified system, we have the AASHTO system, we have the MIT system, we have the ASTM system, and we have USDA system. So for example, unified system classifies the soil to gravel, sand, and fines. The AASHTO system defines the soil to gravel, sand, silt, clay. So if you look at the figures, this story table or this figure, you can see that quite similar classification. Just a few small differences between them. Okay. And we have this also another classification system called soil triangle. The soil triangle is also a common classification system. Okay. And here we can just do an example of how to classify using this this system. For example, if we have a soil has some percentage of sand, percentage of silt, and percentage of clay. So this soil is 30% sand and 20% clay. Sorry, silt and 50% clay. We're just making this example to know how to use the triangle. So if you look here, we have percent of silt, percent of clay, and percent of sand. So if you know this 3%, like this example, we can classify the soil. So how much is sand percentage? 30%. So here, this is the percent of sand. And we can go with a dashed line until we meet. For the silt, we have 20% of silt. So here is a percentage of silt. So here, so they will meet at this point. How much is the clay is 50? So it should be 50 to form 100%. So this is the clay percent. So they will meet here. So what is the classification of soil, of this soil? The soil here lie in the clay area. So this soil is classified as clay. We can have another example. If we have soil of 50% of sand, 10% of silt, and 40% of clay. What is the classification of this soil? Here, in this example, the sand is 50%. So we can go this direction. And we have the silt 10%. So this is the silt 10%. They meet here. So this is the percent of clay. So this is the point. So here is the red area. What is the type of soil we have here? Sandy clay. Okay. So this is two example of soils that we can use the soil triangle to classify. Okay. The system we are using here in Australia is the USC or Unified Soil Classification System, and also it can be known as USCS, which is called the Unified Classification System. In this system, the soil is represented by two-letter abbreviation based on two criteria: the particle size distribution or the plastic of the finer particles, clay or silt. So you can divide or classify the soil based on two criteria: particle size distribution, gravel, sand, silt, clay fraction. This will be applicable for coarse or large particle size. So it can be only applicable for coarse size. The other criteria or the other method is the plasticity of the finer particle. This one is for clay or silt, which means that it is applicable only for fine or smaller particle size. Okay, so we have two methods here: particle size distribution, plasticity, depending on coarse or fine soil. Okay, if we go to next slide. here. So USCC. This table is a USCC system and can be found in the Australian standard AS 1726 217 for the soil tests or geotechnical tests of soil. Yeah. So this one is called geotechnical site investigation. So you can find this table or this classification system in the 1726. Okay, if we look at this table or this figure, so we have grain size or particle size, we have basic soil type, and we have some numbers here or some limits, and we have this border line between the fine grained soil and the coarse grained soil. So this is the first system, or sorry, the first part to classify or differentiate between the fine grained and coarse grained. What is the limit that differentiate between or the borderline between the fine grained and soil grained and the coarse grained? 0.075 millimeter. So these are the size. So we have here 63 millimeter. We have here 2.36 millimeter. So all the dimension in millimeter for this system. And here is 0.075 millimeter. And here is 0.02 millimeter, very small. Okay, so if the size of the particles less than 0.075 millimeter, so the soil is fine grained. And if the size is larger than 0.075 millimeter, so it is coarse grained. We will find this size, the size of the particle, using sieve analysis or some tests in the lab. But anyway, if we have the size of the particles and we need to classify the soil, so we have this border line. If it is less than 0.75, so it's fine. If it is more than 0.75, so it is coarse. And if we look here, in the under the fine grained or this green part here, we have another borderline between silt and clay. What is the borderline between silt and clay? 0.02 millimeter. So less than 0.02, 0.002 millimeter, so it is clay. Sorry, this less. If it is less than 0.02 millimeter, so it's clay. If it is larger than 0.02 millimeter, so it's silt. This means that silt is larger size than clay. If we look at the coarser size, or we have another color here, can have another color here. So in this sky blue, all these are coarse grained soil. We have some limits here. For example, this 63. If the soil size is larger than 63 millimeter, so it is boulders or cobbles, very big size. If it is between 2.36 and 63, so this all is gravel. The sand is between 0.075 and 2.36, which is this area or this part. Okay. So this is sand. and the size of the sand is between 0.075 and 2.36. So using this chart or this table, you can classify the soil to fine and grain soil, and also you can know if it is clay or silt or sand, gravel, cobble, and boulders. There is another subdivision, if you can see, under gravel, for example. Then, for example, we have F, M, and C. So we have fine, medium, and coarse. So for sand and gravel, there is a subdivision or sub-classification. Also using the size, for example, fine gravel between 2.36 and up to 6. For medium gravel from 6 to 20. For coarse gravel from 20 to 63. So using this chart, you can classify the soil. And here in the next slide, this is just clearly how to classify the soil and using the USC system. So using the USC system, Unified Soil Classification System, we have to get 2 letters for the soil. The first letter is the type of the soil. If it is gravel, so G, gravel, S, sand, M, silt, C, clay. So you have to put, for example, G in the first letter. Which size of the soil considered as gravel? From D equal to 2.3 to 63. If you go to the previous slide, you can see this here. From 2.36 to 63 is gravel. And so on. So from the chart, you can find that if the particle size between 2.36 and 63 gravel, less will be sand, less will be silt, and less than 0.002 will be clay. So this will be our first letter. Second letter, we have the grading, the grade of the soil. Okay, so we now know it is gravel, but we need to know if it is poor graded or well graded, and we will explain now what is poor graded and what is well graded. So here, just we need to differentiate between these two classification. Here, B and W are poorly graded and well graded, and this can only be for coarse soil. So it will be only for gravel and sand. So gravel or sand can be poorly graded or well graded. The other classification is for fine soil. What are the fine soil we have here? Silt and clay. So for silt and clay, we have a different definition or different classification. We have H for high plasticity, intermediate for I for intermediate, L for low plasticity. Okay, so for the fine soil, we have 3 sub-classification or 3 second letter classification, and for the coarse soil, we have 2. So for example, if we have G here, so it can be B or W. If we have clay, so it can be one of these 3. Can be high plasticity, intermediate plasticity, or low plasticity. Okay, so this for clay or silt, this for gravel or sand. Now we need to know what is the meaning of poorly graded and well graded. This graph or this slide will show us what is the difference between poorly graded and well graded. If you look at the size of this particle here, you can see that all the sizes are quite similar, so it is uniform size. This uniform size soil is not good for us because it is poorly graded. We need to have different size of soil. So for the poorly graded soil, we give it the symbol B, and we have only limited size range because it's only almost one size. Almost one size. Okay. And to know what is the difference, we need to see the uniform or well graded. Sorry. The well graded, we have all the particles has multiple sizes or all sizes are represented in the soil. So we don't have a uniform distribution of soil, but we have different distribution or different size distribution of the soil. This soil is good for us and it is considered as well-graded soil because we have good range of sizes. We can give this the symbol W. So B for poor graded, W for well graded. And this classification is for gravel and sand. Okay, we have something in the middle that we have different size particle, but some sizes are missing. We don't have a good distribution of soil, so we have some big particles and some small particles. So this also considered as poorly graded soil. In other standard, it can be defined as gap graded soil. Gap graded because some of the sizes are not represented in the soil. So that's why it is called gap graded. But in Australian standard, it is still poor graded or B. And also this only for gravel and sand. Okay. So we have poor graded and well graded only for coarse soil in Australia. The next slide is an example of lab tests. So in the lab, to find the soil particles, the classic way to do that is the sieve analysis. Have you heard about sieve analysis before? Sieve analysis means that we have some sieves with different sizes. For example, from the table, if you look at the table here, this is the like standard sizes of sieves vents. Okay, these are the standard sizes, so we will use in the lab these sizes or this sieve analysis. What you expect to put the larger vent on top or the larger vent on bottom? What do you think? If we put the larger size on bottom, so all the soil will pass through all the sieves, so we will not get any result. What we need to do is to put the larger sieve size at the top. For example, start from 2.63 millimeter and then 0.6 millimeter and so on up to decreasing up to 0.075. This means that when you put the soil, some particles will be retained here, some parts will be retained here, some parts will be retained here, and so on until we reach here. So we have some particles pass through the 2.36, some pass through 0.6, some pass through the next one, and up to retaining the remaining particles will be retained on the 0.075 millimeter sieve. If we draw the relation, we have relation between the grain diameter or sieve size in millimeter. And we have here, sometimes they draw the relation by the percent finer or the percent of coarser, or in another definition of the remaining particles or passing particles. So you can draw the relation between the passing percentage with the grain size diameter. Also, you need to keep in mind that this is a log scale curve. That's why you can see that the vertical axes are close in some areas and far in some areas. This because the size range from 0.01 to 1000. So you cannot draw a normal scale curve between these two values. It will be hard to show the result. That's why we have this log scale. Anyway, if you look at this curve, we have 4 examples of soil. This number 1, this number 2, this number 3, this number 4. What do you think? Which one is poor graded and which one is well graded and which one is uniform? If we look here, for example, number 1, we have some particles on this side, some particle on this side, some particle on this side, but all this area, we don't have any sizes. So this is a poorly graded curve or a poorly graded soil. Number 4 as well, we have only here, all this area we don't have. Also here, it is constant or almost the buzzing, not much buzzing here. So we don't have also good distribution of soil. So that's why number 4 also is considered as gap graded because one of the sizes here is missing. So it can be poorly graded or gap graded. If we look at number 2, so as you can see, most of the particles are around this size. So number 2 is a uniformly distributed soil or poorly graded soil. Okay, so which one is the best one? Number 3. If we look at number 3, we have good distribution. We have but almost all the sizes here. So it distributed over the sizes. So that's why number 3 is considered as well-graded soil or W. Okay, so this particle size distribution curve give us also indication about if it is poor graded or well-graded soil based on or using sieve analysis. Okay. Do you have any question, guys? Okay. Now this is some example of the soil. So if we have gravel for the coarse grained soil, we have gravel. So the primary symbol or letter 1 will be G. And it can be well graded or poor graded. If it is well graded, so it will be GW. If it is poor graded, it will be GB. So GW well graded, GW poor graded gravel. This type well graded soil is unusual in natural soil. It can be artificial, but in natural soil it is not common. The other coarse soil we have is sand. Sand has the symbol S. This is the first letter. Can be also well graded or poor graded. If it is well graded, so SW. If it is poor graded, so SB. Also, well graded sand is not available in natural soil, but it can be in artificial soil. Yes, it is always the material first, the primary classification, the material, gravel, sand, silt, clay, and the second letter is like more specific, like grading or plasticity, depending on if it is fine soil or coarse soil. Okay. So now this for the coarse grain soil. There is another special cases of coarse soil. In some cases, the soil has more percentage of silt or clay. So it is not close to the coarse soil, but it has more percentage of silt and clay. That's why in some cases we have another classification, which is again the primary classification is G or S, the material, gravel or sand, but the second letter will be changed because we have we have high percentage of silt or high percentage of clay. If we have high percentage of silt, so the soil classification is GM. G is for gravel, M is for silt. If it is high in clay, so G gravel, C clay, and so on. So if we have more than 12% of the soil silt or clay, so we need to classify the soil as GM, GC, CM, or SC. Sorry, SM or SC. So this classification only in some special cases and for coarse soil only. Okay. This will be our last slide. We will continue next week. But anyway, here we can stop at the last slide. Okay. Do you have any question, guys? At the previous slide. So we'll start next week from the fine grade soil. Do you have any question, guys? All good? Okay, I will stop recording now, and if anyone has question for consultation, I can help him. And if you don't have question, you can leave the session. Thank you for attending today.